up for Saturday morning.
Yeah, look, we'll have a great Friday when the test scores come out, right? We'll see. So has anyone seen Twister?
Yeah.
You know the idea of Twister? You have this researcher who was trying to get data with tornadoes and has this little thing with lots of balls, and then he tries to drive it underneath the tornado. In the end of the movie, they get it underneath the tornado, and the things fly, and they get all this data. And then presumably they make it seem like that made her career, and she's really happy. That's how I felt on Sunday. Shad knows. I feel like my lab may have had our first, actually our second Twister moment. So excited. Remember, SDSU, I think I was talking to someone earlier today, you guys might not realize this, but SDSU is a research university. We're looked at as in the top 7% internationally as research universities. Our psychology department is one of the top psychology departments in the world. Arguably usually in the top 3 between Stanford and some other schools. So, be proud of being at SDSU, right? This is actually a really good research school. Yeah.
What happened on Sunday?
What?
What happened on Sunday?
Oh, I just got some awesome data.
Oh, cool.
Lots of data. It took me 12 hours to go through, which is always a good. Data analysis is a big part of science for those who don't know. You do the experiment, you get data, and the thing that makes it awesome is when you analyze it and you actually figure out the trend, or a trend you weren't expecting. So that's the fun part of science. Chem 432 exams on both sides are not the fun side of science, right? The fun side is when those who want to be scientists, undergraduates, I hope there was some of you in this class want to become scientists, decide to do undergraduate research. The fun part is when you guys get into an undergraduate research lab and get to do science. And the cool thing about SDSU, just to sell SDSU even more, we're one of the rare research universities that has a huge focus in undergraduate research. So a lot of science majors require undergraduate research for graduation. And so you guys get a really awesome opportunity that not everyone gets to do cutting edge undergraduate research. So those who are interested, definitely find a professor who you like, whose research excites you. I can't recommend more if you're interested in getting involved in research at this level. So at the end of class on Friday, we finished off talking about acetals, and we started talking about what happens with catalytic acid when we add in the mean. Do we form an acetal within the mean? And indeed, we do as an intermediate. But the key thing is with amines, we have a very, very high energy lone pair of electrons on the nitrogen. And bonded electrons are always going to be more stable than lone pair of electrons. That's just one of the dogma of this class. And so what actually happens is we have this intramolecular proton transfer. It gives us H2O, which is a good leaving group, plus. And then it gives us NHR with a lone pair of electrons. And so what now happened is these lone pair of electrons actually kicking off the H2O, giving us an intermediate like this. And again, if you do an acetal mechanism with methanol, for example, to go from the ketone to the dimethyl acetal, we form something like this, a positively charged with an oxygen and a methyl. So just to show you the intermediate with the acetal, so with MEOH, we form an intermediate like this with water, which can kick off water. And this is an acetal, so this is a different mechanism. This is me hearkening back to the acetal mechanism. To draw an analogy between the acetal mechanism and the imine mechanism. So that's why I'm drawing this right now. I have this equal signs to say that. So in acetal chemistry, we form an intermediate like this, and then another equivalent of methanol comes in. And adds in to eventually give us our acetal. So I'm going to box this off because this is separate. This is me drawing an analogy between acetal chemistry and imine chemistry. However, in this case, the difference between this and this is that in this case, we have hydrogen on the nitrogen. Whereas in the oxygen case, there's no hydrogen. So what that means is it's going to actually probably be easier for the water to take this proton to give us our neutral imine, rather than water adding back in to give us our M and out. Acid-base chemistry is almost always going to be easier, i.e. lower in energy, than adding into something. So in this case, water doing acid-base chemistry to give us our neutral imine from this iminium. So the iminium is just an imine with a positive charge. And so that gives us our imine, and that's stable, and that's what we get. And so you could argue one reason why with nitrogen we get imines instead of acetals is because when we form our iminium, which is akin to this intermediate in the acetal mechanism, the water can just go in and take this proton, giving us a stable, neutral carbon-nitrogen double bond. So what happens when we use secondary amines? So, as I say up here, it's probably hard to see, so let me rewrite the primary. We form amines when we use, so this mechanism is at play where we form amines when, and this is reviewed from Friday afternoon, by the way, but amines are formed when we use primary amines or ammonia. So only one substituent that's not hydrogen, or no substituents that's not hydrogen. So we only form amines with ammonia or primary amines. With a secondary amine, we form an iminium intermediate by the same mechanism, nothing changes. The only thing that changes is now, when we form our iminium, there's no hydrogen for this water to take off, right? There's no hydrogen. So what that could mean in theory is that, well, then maybe water's going to add here and give us our acetal-like thing. But, and this is a big distinction between this and this, is even though there's no hydrogen and a nitrogen to give us a neutral compound, there are these hydrogens on the carbon adjacent to the double bond. And so in theory, these hydrogens are in conjugation with the positive charge. So what happens, instead of the water adding in, like it would in this case, the water instead will take this hydrogen, kick into here, and have these electrons go to quench the positive charge of the nitrogen, and that'll give us this carbon-carbon double bond, which is adjacent to a nitrogen. And so this we call an N-amine. So N, double bond is N, amine, amine. So an N-amine, or an amine adjacent to a double bond. So the take-home message from the last part of lecture on Friday was really, amines in most cases don't normally give you acetals. They can in special cases, but they don't give you these tetra-substituted sp3 carbons that are acetals like with alcohols, or oxygen-based heteroatoms. What they do is if you have a primary or ammonia, you get an imine. If you have a secondary amine, you get an enamine. So just to give you some real world examples. Does anyone know what this is? This is a famous amino acid. Does anyone know what amino acid this is?
Proline.
Proline, thank you. Someone took biochemistry, right? So you can take proline. And so this is our amine. And now I'm going to take acetal. So does this reaction need catalytic acid? They normally need acids. But does this reaction need catalytic acid, or is there an acid already present? Yeah, there's a carboxylic acid, pKa4. So the carboxylic acid is acidic enough for this. But this is one of the rare reactions where you don't need catalytic acid because it already has the acid. So of course, this will go through this mechanism and eventually give us an imine. Of course, each of these methyl groups has 3 hydrogens. But there's a positive charge here. And of course, when this adds into the carbonyl, it's going to give up H2O. So just like in this step, it's going to do something just like this. And it's going to give up H2O. And so since this is now a secondary amine and there's no proton to deprotonate, it's going to deprotonate these hydrogens that are adjacent to the carbonyl. So these 2 electrons that were here are going to go dump into this bond, causing the electron density in one of the pi bonds to go jump to the nitrogen, quenching it, giving us a nice enamine. So this enamine we form, is this an electron-rich double bond or is it an electron-poor double bond? Excuse me? Yeah, it's very electron-rich, right? Because this is an amine is very much electron-donating group. So this is a very electron-rich double bond. So it will act, if we tried to do this with a Diels-Alder, it would be a lousy Diels-Alder dienophile because this is a very electron-rich. Yes?
Did you say, so I'm wondering why the OH is still there. Oh, because it's catalytic on the...
Yeah, on the acid, yeah.
Sorry.
But if you wanted to draw a form where the nitrogen takes the proton and the OH, we'd have to think about that carefully because what's the hybridization of this nitrogen? sp2 or sp3? sp2, right? It's a nitrogen adjacent to a double bond, so it can resonate. So if a hydrogen is adjacent to a double bond, it's going to be sp2. So this is an sp2 nitrogen now, and sp2 nitrogens are going to be a lot less basic than sp3 nitrogens. So then as far as equilibrium between the proton being here or the proton being here, we have to take into effect that this isn't a typical tertiary amine. This is a sp2 tertiary amine, and it's not going to be as basic. Yeah?
What's that R on top of the middle one?
The R. This guy right here?
On the left of it.
It's like an upside down L.
Yeah, upside down L.
Where is there an upside down L? Oh, this guy. Intermediate. Brackets, intermediate. Sorry, I thought I'd drawn this along in the class as brackets. Sorry. Brackets, is that better? Chemists don't get lazy and don't draw the entire brackets all the time. Yeah.
That's why proline is a helix breaker.
Well, proline is a helix breaker because it's a ring, and so proline is pure. So usually we can have some flexibility in the amino acid backbone, but since proline is cyclic, that kind of forces it into a conformation that isn't simpatico with helices. But that's a very interesting biophysical question. You should ask Professor Hexford that if you ever have a class with him. Okay, so the key thing is with secondary amines, we get enemies. And I hope this mechanism isn't too crazy. The key thing is it's going to add and kick off water eventually through a mechanism that's very similar to the acetal mechanism, giving us this iminium, which then will protonate one of the hydrogens to get an imine. And the reason that I see a lot of like smirks. And so when I see smirks, I get worried. I get worried that half the class doesn't get what I'm talking about. And if so, I need to know so I can go over it again. So should I be worried about all this? Yes.
Can you show the first step how you get to the?
Oh, go from here to here?
Yeah.
Well, it's just, the best thing I can do is just harken back to this, because it's the exact same mechanism. It's the carbonyl gets protonated by the catalytic acid, then the amine is going to add into the protonated carbonyl to give us this. Then we're going to have intramolecular proton transfer, or the OH that formed from addition is going to take a proton from the amine. And we can argue this by pKa, right? Because, ammonium has a pKa of about 10, so this is fairly acidic. Of course, the equilibrium is going to slightly favor this, because in this equilibrium, the OH2 plus is going to have a very low pKa, right? So equilibrium almost always sides with the weaker acid, and the weaker acid is definitely, in this case, ammonium rather than oxonium. But nonetheless, as we discussed last week, equilibrium is complex. You can have one step later on downstream in the synthesis that can affect the synthesis. And so what that means is, where the equilibrium is going to favor this, when we form this intermediate, we can kick off water as a leaving group. And kicking off water is always favorable. And so then, whereas this equilibrium is not going to favor this equilibrium is going to favor this direction. And so by Le Chatelier's theorem, right, if we remove this by quickly doing this, then the equilibrium is going to shift towards this unfavorable intermediate to regain equilibrium. And so that's going to cause everything to funnel through this, and then the water takes the proton to get the amine. Of course, with the secondary case, this is in our group, so we can't do the proton. So it's got to take one of these protons. Does that answer your question about the mechanism? Again, this class has a lot of variations on the same thing. So getting to the imine versus iminium with a primary or a secondary amine, the mechanism doesn't change. It only changes when you get to the imine. And then you ask, all right, we have a nitrogen with a positive charge. Do we have a hydrogen that deprotonated on the nitrogen? No, we don't. Okay, then we must have to take hydrogen adjacent to it. So I didn't redraw the mechanism, but you guys see how this mechanism is still at play to form this? Nothing really changes? Who asked that question? Does that help?
Yeah, so it's going to take the hydrogen off the carboxylic acid.
Yeah, that will act as a catalytic acid.
Okay.
So we form this, and this is an electron-rich double bond. And so, just to give you an example of how electron-rich it is, if you take an electrophile, like an aldehyde, it will add in the aldehyde at this carbon. To give us an alcohol. So, because this double bond is adjacent to a nitrogen, and of course there's a positive charge on this nitrogen now, because of this electron-donated group, and amines are electron-donated groups adjacent to the double bond, and amines are quite nucleophilic at this carbon. And you can be able to predict this by drawing a resonance structure of an amine. Or if you have these electrons kicked down here, but instead of attacking the ester, go into this bond, that gives us a discrete minus charge by resonance. So you can pretty much, using resonance, once again, predict the reactivity of something you've never seen before. And in this case, by drawing a resonance structure, we can predict that an amine is going to be very nucleophilic at the carbon and be able to attack many electrophiles. So let's keep talking about enamine chemistry, but now let's try something a little bit different. So here is an amine where its substituent is an oxygen. Which one of these two things under catalytic acidic conditions is going to attack the carbonyl? The nitrogen, right? Nitrogen's going to be more nucleophilic than oxygen any day of the week. So once again, to show you the mechanism really doesn't change at all, we're going to protonate the carbonyl. Then the amine's going to add. Then we're going to have another proton transfer. To give us an oxonium, and of course we have the same equilibrium problem we had before, but that's fine because in forming this intermediate, as always, we form water, which is a really good leaving group, and so we can save this lousy equilibrium by having this unfavored equilibrium intermediate quickly kick off water. To give us our imine. Then of course, the water that we kicked off here can act as a base, regenerate our acid catalyst. They give us these things, and we call these things oximes. And oximes are interesting. Do you think an oxime is going to be more or less stable than an imine? Yes. Yes. Why is an oxime going to be more stable? Thank you. High five. Exactly. So we can draw a resonance structure that now gives us an unoxygen double bond, oxygen plus possessed hydrogen, and a minus charge at the carbon. And then, because of this resonance structure, we can actually imagine the minus charge carbon taking a hydrogen, giving us, not having to draw an equilibrium error now, because we're breaking a bond, so it's no longer a resonance structure.